Explain whether the given model is a polynomial or not. Here are some very interesting examples, and I find them very challenging, right? So this is a set of questions which I've taken from a question paper. Now you need to explain whether these represent a polynomial or not. Well, let me remind you what a polynomial is. Polynomial as such can be written as, let me write it here, f of x is equals to an x to the power of n plus an minus 1 x to the power of n minus 1 plus so on, like a2 x squared plus a1x plus a0, right? Is the sum of these terms where n is a non-negative integer, correct? That means it can have values like 0, 1, 2, 3, 4. It cannot have negative or fractional rational values, correct? An is called the coefficients for x. An is the leading coefficient, and that's the constant, right? And an belongs to a set of real numbers. So these are the coefficients for these variables, and this equation is in single variable, correct, of degree n. So we have a polynomial of degree n represented as an x to the power of n plus an minus 1 x to the power of n minus 1 and so on, right? So there could be terms missing in between or whatever, right? And even a constant term, if these terms x are 0, for example, and we just have a0, then also it is a polynomial. Remember that, right? So it becomes a constant polynomial. And if we have just these two terms, or kind of up to here, there's a linear, right? Like y equals to mx plus b type. And if it is here, it's quadratic and like that, right? And that's the degree of the polynomial. Now, look at the examples below. I'll fill in E and F. I'll just draw a sketch of a graph there. And try to answer the questions. I'll give you time to answer before I give my answer, okay? Now you need to explain if it is a polynomial or not. Well, if it is not a polynomial, then you should give more explanation for it, right? Even if it is, then also. Now a is y equals to 1 over x to the power of minus 6. Now is this a polynomial or not? So you may have to rework at times, correct? So here you can write this as, look at this could be written as x to the power of 6, right? So if you write this as x to the power of 6, then what do you think? Is it a polynomial? Yes, the answer is yes, correct? So yes, it is a polynomial, correct? Now let's look into example B. F inverse of x, where f of x equals to plus minus square root of 2x minus 1. So is it a polynomial or not? Well, fx equals to plus minus square root of 2x minus 1 is clearly not a polynomial, right? You cannot have square roots and things like that in polynomials. But we are talking about f inverse of this, right? That's why I made it like bigger and bolder for you, so that you should focus on inverse of fx, not the function fx given to you here, right? Well, which is not a function also. Anyway, so what is inverse of this? You have to look into that, whether that is that model, whether that model is a polynomial or not, okay? So let's find the inverse of this, right? Inverse we can find by reverse calculation, correct? You remember my video on finding inverse by reading your equation in backwards and doing the reverse operation. So let's do that. So basically, if you see the equation, it is plus minus square root of 2 times x minus 1. If I read it from here, I can square first, right? So square, so I'll write x square. And once I square it, then I will say plus 1 and then divide by 2, right? Plus 1 and divide by 2. So that becomes my f inverse of x, right? So this is my f inverse of x. Let me write this as f inverse of x equals to this, which is a quadratic equation, correct? So I could always write this as half x squared plus half, right? Now that is a quadratic equation, right? So that has to be a polynomial, correct? So we'll say yes for this also. But it's important to see it that way, right? Before you can answer it. And that's the explanation also, correct? Now c is like a rational function. Y equals to 2x minus 3 times 3x minus 6 divided by 2 minus x. And also exists at 2 minus 3. Now think about it, whether this is a polynomial or not. At first glance, it looks like not a polynomial, because in polynomials, you can't divide. There cannot be anything in the denominator, right? But this is kind of tricky. Let's try to reduce it and simplify it. So you can take 3 common, correct? So if you take 3 common here, then what happens? Then this could be written as 2. So I'll write 3 first, right? So I'll write 3 first and write 2x minus 3. And within brackets I'll write, because I took 3 common, right? So we can do x minus 2. X minus 2 over 2 minus 6, correct? Now fine, and clearly it has a restriction that x cannot be equal to 2, but we have given here that it exists as 2, so you can always superimpose, right? So it's a function which is for all real values, that is the function, but for x equals to 2 the value is minus 3. Now this could be simplified further, right? So we could cancel this out and we get minus 3 times 2x minus 3, right? And of course when this happens, we write that for this rational function x cannot be equal to 2, right? So for this particular thing, x is not equal to 2, but we are given this additional information that add to the values minus 3. So what we need to check here is that if we plug in 2 here, what do we get, right? So let's plug it in. So if I write 2 here, I get 2 times 2 is 4, and 4 minus 3 is 1, and 1 times minus 3 is minus 3. So actually so there is a hole here, right? When you cancel this out, then it results into a hole, right? So this function results in a hole. Now that hole is plugged in, right? So this hole is plugged in by the value 2 minus 3, right? So it becomes a continuous function, correct? So, and what is this looking like? This is like a line, correct? So where we have minus 6x, so I can write this as, let me write this here, minus, open the bracket, that is, minus 6x plus 9, correct? Minus 6x plus 9, it goes with our definition clearly, and it is continuous because the hole has been plugged by 2 minus 3, right? And therefore we say yes to this also, and this is also a function, correct? So that is how you have to see it and explain it, correct? It's kind of complicated. Now D is x equals to 15. Now is that a function? Will you call it a constant function? X equals to 15. So look at it carefully, right? It is not y equals to 15. It is not f of x equals to 15. This represents a vertical line, right? This represents a vertical line at 15, and that is clearly not a function, right? So here we say no, it is not a polynomial, okay? So the question is, explain whether the given model is a polynomial or not. So this is not a polynomial, that is also not a polynomial. This and the previous 3 are polynomials as we have written, right? But here x equals to 15 is not a polynomial, right? It doesn't go with our definition at all. It has restriction on domain. Polynomials don't have any restriction on domain, and therefore we will give our reason on this as restricted domain. polynomials don't have any restriction on domains, and that is one reason which we could give for this. And here for you, I'll just draw two models, and then you figure it out whether those are polynomials or not. Okay, so one is like this. It's like an absolute function. Okay, now you have to reason out whether this is a polynomial or not. Well, and think about this. We have another function which looks like this. Now, see whether this is a polynomial or not. Okay, so think about it, and then I'll give you my answer. So, what do I think? Well, this is not a polynomial. And what is the reason? We are not given any equation, so we can't really compare it with the equation, but we are given a graph here, and the graph clearly shows a corner here. In a polynomial, in the graph of a polynomial, we can never have cusp or corner, right? Cusp or corner, right? So that is the problem. And here we have a corner, therefore it is not a polynomial, correct? Not a polynomial because it has a corner, okay? Polynomial graphs cannot have any cusp or corner. I hope you understand what is a cusp. It's a good point to explain here. Like this in a graph, if you have, this is a cusp, right? And we cannot have this cusp or a corner like that shown, right? Many functions like radical roots, right, will have this kind of a sketch. Now let's move on to the last, f. This graph, what do you think? Is it a polynomial? And if it is not, what is the reason? Well, this polynomial is actually has a restricted range, right? It is kind of wearing off like this, and this is clearly not a polynomial. And you'll find the sketch like, if you do cube root of a function like that, then you may get a sketch like this, right? So this polynomial has a restricted range. Right? It is not really going towards the infinity. So we'll say that the end behavior, so I should not write really restricted range, because if you do, it can go up to infinity, but the end behavior doesn't match. End behavior doesn't match with polynomial, right, graph, with polynomial graph, and therefore this function does not represent a polynomial, right? You will get these kinds of graphs if you look into functions like cube root or root like x cubed. Then you'll get this kind of a graph for the function, correct? So it does not represent a graph of a polynomial, correct? So that is how it is. Thank you.